Okay, so good morning everyone. Let me get started today. The first thing I want to mention to just keep in everybody's mind is that right now we are week 12 already, right? So time flies so fast. I remember recently we were just commenting that we are at week 5, the third of the semester. Now we're at the last 1/3 of the semester. So we are here today, and next week we have one more quiz, and 2 weeks after that we have the assignment due. So yeah, right, some of you already started working on the assignment. That's good. And our next quiz, we will do it in the same way, so Wednesday to Thursday, and then same style, everything the same. The topics that we will cover in quiz 3 will be chapters 8 and 9. So what we will discuss today, this week and last week. Okay, so I will send the proper announcement later on the Moodle, so you will get the email. But right now I just mention it, so just so to have it in mind. Okay, yeah, right. So today we are going to talk about the wave equation. So yeah, usually in quantum mechanics we represent the wave function as psi. So that one is in quantum mechanics. And but what we're doing today is not yet quantum mechanics, but a lot of other things also will set are wave functions. And I'm going to call them f today, and as a function of y. So let us see how this works. Okay, so what is a wave equation? What I'm going to talk about today is specifically propagating wave. Sometimes it's called the traveling wave. Right. So in our previous class, I just started to explain to you what is a wave, right? Wave is a disturbance in a medium. So the medium can be anything, whether it's a water or a guitar string or air, right? Or quantum fields or anything, right? So there's many possible mediums. And then if you cause a disturbance, the disturbance will spread throughout the medium. So if you drop a rock into a water, right, it will cause the wave inside the water. The water wave will start to spread around. So that is a propagating wave, right? So traveling wave. Later in this chapter also, we will talk about how light is also a form of wave. We will calculate the interference of light. We will only touch upon this very briefly. We will spend more time on this in the next semester for light. But right now we're focusing on water waves, strings, and things like that. Okay, so how do we explain propagating wave? So propagating wave is remember, right, the key point is disturbance that spreads throughout the medium. So we have learned two types. Transverse wave, the direction of disturbance is perpendicular to the propagation, so disturbance like this, propagation like this. And then longitudinal wave is the direction of disturbance is parallel to the spread. So I've drawn you the picture at the end of previous class, right? So whether it's transverse or longitudinal, right, the amount of displacement, I call this y, right? So yeah, the sound wave, right, the amount of displacement, I call this y, and then x is the position. And then I can plot the graph of the disturbance for different locations at different times. So at time 0, let's say I have this type of wave. Okay, right now let us treat this as a mathematics first, right? So let's say I have a graph. So let's say I have a graph, right, and then the shape of the graph is like this. So this graph is a function of x, right? So for different position x, I have a different coordinates of x and y, right? And everyone learned this in calculus 1 already, right? At the beginning of calculus 1. Okay, so this is at time 0. But as I said, right, wave is something that propagates over time. So that means at different times you get a different graph. So at a later time, right, let us suppose that we are talking about a propagating wave. So if a propagating wave, let's say the whole thing will travel to the right, okay, and let's say at some time t later, the whole shape of the graph has moved to the right. So originally my point is over here, right, and then at some later time my point has moved to the right over here. Okay, so if t is the time, and then the displacement is vt, so the v is the speed of the propagation, right? So right now we're assuming constant speed. Okay, so this is the shape of the graph. So what is happening here is that so the graph, right, so in this situation graph has moved to the right, and I'm talking about to the right relative to the axis, so relative to the y-axis by distance vt. Okay, so assuming v is positive, and then if it's moving to the right relative to the axis, but if you are the wave itself, that means the axis has moved to the left from the graph, right? So this is something like relative motion. So we say that axis has moved to the left relative to graph. By distance vt also. Okay, so vt is the magnitude, right? So that means, right, this is why the graph is originally is a function of x, but then if I shift it to this, then my new function should be x minus vt, because the axis has moved to the left. So my new x coordinate, right, the reason why is minus vt is the original coordinate, because it's moved to the left, so it's minus vt. So my function has become the function of x minus vt. Okay, so can you agree with this? Or do you have any question? Because I'm sure people have any question, because the first time I was learning this, right, I couldn't understand why is it minus vt and not plus vt, right? So it took me a long time to understand, but it's actually minus vt, right? And it probably make it easy to understand if I show you an example, right? So let's say I have an example. Let's say my function is x squared. So if I draw my graph at time t0, okay, so how do you draw the graph at t0? So t0, the function is x squared. So then I have this, right? So this one is no problem, right? So this is y is equals to fx, so y is equals to x squared. But then at some later time t, if my graph has moved to the right, right? So if my graph has moved to the right, okay, let's say now is 5. So now my graph is now here. So how do you draw the equation of the graph, right? So the equation of the graph is y is equals to x minus 5 square, right? So if this thing has shifted over here, then it should be x minus 5, right? Because when x equals to 5, my graph is 0 point over here. Okay, so it's minus for a graph that's moving to the left. Then we can easily get the same argument if my graph is moving to the right. So let's say negative 3, right? So it's negative 3. If it's over here, then my equation now is y is equals to x plus 3 squared. So if it's moving to the right, I minus vt. If my graph moves to the left, I plus vt relative to the axis. Okay, so this is how we explain the propagation of the graph. Okay, so does anyone have any question? Yeah, I think so, because I will talk about the wave equation, and then if we reach the standing wave part, I can demonstrate all the tension of the string using the guitar. Left is plus, right is negative. Yes, yeah, correct. Correct, yes. This is how I understand it. Yeah, so x minus vt 0 is the original point. Yeah, so if I follow my original point, right, my original point is, let's say I choose this to be my original point, then my original point is now here, right? So I want to make this 0. Yes. So yeah, good, right? So you guys are already more ahead than me in understanding when the first time I myself is learning it. Yeah. So the first time I couldn't understand, right? Then I end up memorizing and memorizing. So it's like oh, like this means minus, then the other way means plus. It works, but it doesn't help in like getting the feeling of like understanding what is happening, right? When it comes to memorizing. Yeah, coordinate axis is moving. Yeah, so the way I finally understood it is this second line. The axis moved to the left, because we imagine the graph moving to the right, right? So that's the good way to understand the situation. Okay, so yeah, so that's where we are now. Okay, so yeah, so now So now that we understand this picture, right, so let me finish off this description by considering the propagation towards the left. Okay, so since I think thanks to this picture alone is quite straightforward, so let me quickly do this propagation towards the left. The left. Okay, so propagation towards the left is, let's say my original graph, I draw the same original picture again, right? So let's say my graph is at time 0 is like this, right? So this is at time equals to 0, and then at a later time, let's say if I'm moving to the left means this graph is now here. Okay, so my original point has moved to the left, right? So the distance is, let's say, vt, right? The distance is vt, so the coordinate, the position here is negative vt, right? So this one is where the graph, this is where time is greater than 0. So graph move to the left, relative to axis, and then therefore the axis has moved right relative to graph. Okay, so then this is my x new is equals to my x original, and then I have plus vt. Okay, so if originally y is some function of x, then if I'm moving it to the left, then y is equals to fx plus vt, right? So v is the speed of propagation, right? So whether it's moving to the left or moving to the right, is the velocity will be positive or negative, right? So let's call this v the speed. Okay, so that is how we understand the wave propagation, right? So that is what we want to study today. Okay, so yeah, so I guess everyone is following so far. Okay, so now let us be more general, right? So this is a special case x minus vt, and now let me write a general equation for a propagating wave. And what I'm going to do is I'm going to derive a differential equation satisfied by the wave. So I will tell you more about it when we come to that point. But let me say that let me write down the general solution first. So more generally, okay, so we consider functions of the form okay, f of u. Okay, so f of u is given by f of kx minus omega t. Okay, so in other words, my u is equals to kx minus omega t. Okay, so this is a two variable function. Of x and t. And then k and omega are constants. Okay, so this equation will describe a wave that is, if I let's say consider k and omega they're constants, but let us take them to be positive constants. So if I have a minus sign, right, minus sign, then I have the graph that is moving to the right. If this is a plus sign, I have the graph that is moving to the left, right? So everything is the same here, just that in this picture my k is equals to 1, but generally speaking k can be any constant, right? So we will include the constant there. So how do we calculate the speed of the wave, right? So this is a wave equation, right? So let's call wave equation, wave function. Okay, so wave equation usually refers to the differential equation. So this is a wave function, right? And it describes a graph. So it's described that a graph that is, so it describes, where should I write this? I should write this here. Describes a function whose graph is moving, right, towards the left or right. Basically, I'm just repeating what I said because I try to convince you that this graph is moving to the right. So generally this is what we are having over here. Okay, but from this, right, how do we calculate the speed of the wave? So we can actually have a formula. So how to get the speed of the wave? Right, so to get the speed of the wave, right, like just like what we've been discussing last time, we just now, right, we trace the original point and see how fast it's moving, right? So we trace one point and we follow this point and see how fast it's moving. So what we do is we track the motion of a specific point on the graph. Okay, so let's say yeah, so my point is like this. Okay, so let's say I follow this point, right? So I'm calling this point P, right? So the height of this graph is let's say f of u, and then my horizontal axis is my x-axis. So my coordinate is u0, right? So u is just the short form for all this. Okay, so my u0 is just a short form for kx minus omega t, right? So the x, right? So the x is the actually f of u. This one should be x because this is the x coordinate, right? So this is the x coordinate of point P. Right? And then so let me rearrange. So I got kx is equals to u0 plus omega t, right? So this is my x coordinate. As t goes on, right? So as t goes on, the x position will change, right? So but for this one instant, my x happens to be here. Then my function of fu is given by over here. Okay. Chain rule. Well, I haven't done chain rule yet, but I'm about to do it for fx. What do you mean? Stomach pain? You mean like you went toilet and missed something, is it? So nothing. So kx minus omega t, right? And u is just a short form for writing all this. Yeah, not a cold, but I sometimes when it's dusty, my nose will become like this. Okay. Yeah. So let me rearrange, and as you can see now, right, I'm about to do something to calculate the velocity. Okay. So to get the velocity, right, this is the x coordinate, and the x coordinate is changing with time. So this is basically what we always do, right? Once we know how the x coordinate changes with time, we can differentiate to get the velocity, right? So the velocity is dx dt. So v is equals to dx dt. And basically I differentiate this, right? So differentiating this, this is a constant, differentiate 0. Differentiate t becomes 1, so I got omega over k, right? So from here I found that v is omega over k. This is my wave velocity. Okay, so this is my wave velocity. Wave velocity. Okay, so wave velocity means it is going to the right if v is a positive number, and it is going left if v is negative number, right? So it depends on omega and k. Okay, so if I take the modulus, the modulus omega k is it will give you the speed. Oh, you also same problem with me, is it? The nose problem. Yeah. I also don't know how to solve this problem. Maybe just to clean up the house a little bit, or some medicine related to this. Okay, but so I hope no one missed anything related to this. Is that this is an equation that describes a wave that is moving to if k is positive, omega positive, negative sign. This is describes a moving wave, right? So it describes a moving wave. This function could be any function of u, right? So I have drawn one specific example of x squared, right? It could be any function. It could be sine, it could be exponential. Actually, we will consider sine, but in any case, whatever function this is, right? If your input is kx minus omega t, right? If your input is kx minus omega t, then I have a graph that is moving, right? Then the velocity is going to be given by these expressions. Okay, so this f of u is any function of u. Okay, so this is the basic property of the wave equation and a wave function. So all wave functions satisfy a wave equation. So I'm going to derive of the derivation of the wave equation. So this part, right, is might be scary to you guys because you guys have been complaining about partial derivatives last time. So I'm going to do a lot of partial derivatives later, right? But so if you don't follow, don't worry too much about it. It's just to convince you guys, right? So if you don't understand, never mind. But at least I will show you, must at least show you once, right? Where does the wave equation come from? Okay. Then once we see the wave equation, we know that functions, all kinds of functions like this, they always satisfy the wave equation. So I'm about to show you the derivation of the wave equation, right? So wave equation, right, is looks like this, right? So I have considered functions of u, and u is just a shorthand for kx minus omega t, right? So f is just any function, right, that you learn in calculus. So that means u is is a short for kx minus omega t, and then I want to do the partial derivatives of this. That means like Zirui was saying, I'm going to use the chain rule. So u is a function of two variables, x and t, right? K and omega, they are constants. So I can differentiate u with respect to x. Okay, partial derivatives, right? So partial derivatives, but this part is very easy because there's an x here, t no need to differentiate. So if I differentiate x, I just get a k. If I differentiate u with respect to t, I get negative omega, right? So these are just the partial derivatives. So now I'm going to take the partial derivative of f and see what happens. Okay, so partial derivatives of f gives me what? So let me differentiate this with respect to t first. Okay, so if I partial differentiate this with respect to t, right, so I'm going to use the chain rule. So chain rule means I differentiate f with respect to u, and then by the chain rule I must continue differentiating u with respect to t. Okay, because u is the input here, right? So f of u is like chain rule, right? So this is chain rule. Okay, so what is df du? Df du is unknown because it could be any arbitrary function. So let's keep it like this first. But partial u partial t is negative omega. So in other words, my partial derivative of my function with respect to t is omega df du, right? So df du. Now this df du, right, is another function of u. Okay. So what happens if I differentiate this again? So if I differentiate this with respect to time again, right, this is a constant. So constant no need to differentiate. So what I'm doing is I'm differentiating df du. Okay, so how do I differentiate df du? So that means what I'm doing, right, is remember df du is a function of u. Okay, so if I differentiate a function of u with respect to t, I still need to use the chain rule. So this is omega. That means I need to differentiate this function with respect to u, and then I use the chain rule. Okay, so what is this function of u? This function of u is this whole thing, right? So I'm calling this the function of u. So the whole thing is this. So that means what I'm doing is I need to differentiate with respect to u of df du, right? And then what happens here? So on this part, this is the du dt. So du dt is just negative omega. So at the end of the day, what do I get? So omega is just positive omega squared. differentiate a function of u again. So this is a second derivative. So this is a second derivative of f with respect to u. So this is the partial derivative of f with respect to t. Do you agree with this so far? Correct, correct. Because I'm differentiating t again, right? So I'm differentiating t again, but this is a function of u. So chain rule a second time. Chain rule a second time. That's why I got this thing. And this thing is negative omega. And this one came from the first time differentiating. Okay. Yeah, so this allergic thing, I need to hang on. Let me clear my nose for a bit. I'll be back. Okay, do you get it? Yes. Why is the function of u is df du? Because I mean this whole thing, right? So let me I plan to do it in a second way, right? Let me write it in a different notation. So this one is partial derivative of f with respect to t. So now I want to partial derivative with respect to x. So I'm going to differentiate with respect to x, and then I show you a slightly different way of writing it. So see if you get it. Differentiate with respect to x. Okay, so I have my function, right? F of u, and then my u is equal to kx minus omega t. So let me try to differentiate this with respect to x. So differentiating this with respect to x is, again, I will use the chain rule, right? So x and u are different variables, right? U is another function of x, is this. So this one is calculus chain rule, so df du, and then I partial u, partial x. Okay, partial u, partial x, and then partial u, partial x I have shown you above is equals to k. So this is df du times k, right? So let me write this nicely. That means, in other words, the first derivative with respect to x is equals to df du. Okay, so again, right, df du is something that you differentiate with respect to u. So you take a function, you differentiate already, you get a new function, right? So this is a function of another function of u. So I'm going to let g of u is equals to df du. Okay, so I'm going to let this. That means what happens? That means I have partial f partial x is equals to k times g. Right? Then you go partial d. Yeah. Huh? Wait, I continue first. I think it will be clear after I finish. After I finish this, because every step is like supposed to be nothing new, right? Chain rule, and then this one is I just call this whole thing g, right? So it's easier to understand. So I'm just gonna call this whole thing g, right? And then so it becomes equals to kg, and then I differentiate this one more time. So g is a function of u. So if I differentiate this one more time, k is a constant. So k is constant. So I'm going to differentiate g with respect to x. But g is a function of u, right? And then this is differentiating x. So u and x, different variables. I need to use chain rule. So k is chain rule, right? So chain rule means dg du, and then by the chain rule is partial u partial x. Okay, and partial u partial x was k, right? Because I have shown you earlier that this was k. So this is actually k square dg du, right? And what is g? What is g? G itself is df du. So that means what I need to do is k square d du. I'm differentiating df du. So I'm actually differentiating this function with respect to u. So it's the second derivative. So partial f partial x squared is equals to k squared d2f du squared. Partial u partial x is same as du dx. Not necessarily, because the straight d is for single variable function. The partial is for two variable function. So my u is a function of two variables, x and t. So that's why I use the partial and not the straight d. Yes, correct. Yeah, correct. So the f is, at the moment, it could be anything, right? That's why I said if you don't follow, never mind. Actually, if it's more of a concern for you in calculus 2, right? But we are not doing calculus 2 now. I just want to derive the wave equation. Okay, so you learn this in calculus 2, all the partial derivatives. But what I want to show you is to derive the wave equation. So I got two equations here, right? So equation 1 and equation 2. I'm going to divide the two equations, right? So let me divide the two equations. So I'm going to take equation 1 dividing by equation 2. Okay, and then on the left hand side, right, is partial f partial t. And then on the right hand side is partial f partial x squared. And then on the right hand side is omega squared d2f du squared. And then on the right hand side, dividing this, is k squared d2f du squared, right? So you don't follow also, never mind, because at the end of the day, right, the df du will cancel each other, right? So df du will cancel each other, and then this part I bring it to the right, and I'm going to have the second derivative with respect to t is equals to omega squared over k squared, second derivative with respect to x squared. Okay, so this is what I want to show you. And then as you recall, right, remember that the v is the omega over k is the speed of the wave. I've shown you just now, right? So v omega over k is the speed of the wave. So if you remember this, then I got the differential equation satisfying partial x partial t squared is equals to v squared d2f d partial x squared. Okay, so yeah, again, right, if you don't follow, never mind, because is for those who have not take calculus 2 yet, are not very used to partial derivatives yet, never mind. But what I want to show you is the wave equation. Okay, so all the function, the wave function, right, they satisfy this differential equation. Okay, so that is what we want actually. Can kind of see it, okay, that's good, that's good. So f is a coefficient, no, it's a function, right? The last two step is, which last two step? Dividing equation 1 and 2, you mean? So just now, right, my calculation, yeah, the cancelling is very satisfying. That's kind of the main reason I'm showing you. Yeah, because most of you guys are first year, so all this math are new to you, right? So just now I'm differentiating f with respect to t twice. I got equation 1. And then I differentiate x, I get a second equation. Then the last step is I'm dividing the two equations. I take equation 1, divide by equation 2. Right? So I divide, I cancel these two equations. And then and then after I cancel, this thing I move to the right. So after I move to the right, it comes here. So I got this equation now. Right? And then this was, you recognize something as the speed of the wave. So we got the wave equation over here. Okay, So this is the first time you have seen the wave equation, right? So yeah, this is why I just want to show you for the first time. If you don't follow, never mind, because we just want to use this. Actually, we just want to use this, and also the fact that my function is kx minus omega t. Okay, so yeah, so let's if you're not convinced, right, let's try an example, right? So just now our example was let's take f of u to be u square, right? So f of u to be u square, that means at time equals to 0, right? Then my f of u is just k square x square, right? So k square x square. Then my graph is just looking something like this, right? So yeah, so k square x square, right? I don't know. Then at some later time greater than 0, so my f of u is equals to kx minus omega t, the whole thing square, right? So it has moved to the right. Something like this, right? So and then you can calculate at this point, this is x is equals to omega over kt, right? So it is where this function becomes 0, right? Then let's differentiate this function with respect to t twice. So my f is of u is equals to kx minus omega t. Indeed, yeah, let's put it in this side. Okay, so because at this, when I was deriving this, right, this f could be any function. Now I do this specific case where the function is just square. So let's differentiate f with respect to t. So differentiate f with respect to t, I got 2 kx minus omega t, and then the chain rule gives me a negative omega, right? So and then I differentiate t again. So all these are constants, so I get minus 2 omega. Differentiate this, I got negative omega again. So at the end I have 2 omega square, right? So this is differentiating t twice, and then let me differentiate with respect to f. So differentiate f with respect to x first. So I differentiate this becomes 2 kx minus omega t, and then times k, right? And then if I differentiate this one more time, so this is a linear function, so this is a constant, and then if I differentiate this, I just get a k, so this is 2k square, right? So then let me take equation 1, divide by equation 2, let's see what happens. So partial f partial t square divided by partial f partial x square is equals to 2 omega square over 2k square, cancelling. So I move this up, I got partial f partial t square is equals to omega square over k square partial f partial x square, and this one was your v, so I recover my wave equation over here. Okay, so that is how we can yeah, so that is for the specific case. So any function of u is going to satisfy the wave equation. So I guess you get what I'm saying, what I'm trying to do, right? Yeah, we keep f not to say hidden, but f can be anything, right? Any function, as long as it's a function of u, right? And then the last two steps, multiply both sides with partial. Not multiply, that means I differentiate both sides of the equation. The amplitude, yes. No, f of u is a function of u. It's not amplitude times u. Where did we get the kx again? Kx is, I think for our purposes, let us remember that this is the formula for the wave velocity, right? So how did we get the wave equation, right? So how do we get the speed of the wave? We were tracking, we track the motion of a specific point, right? So we got this, and then we just yeah, right? So x is a linear function of t. That means the the position of this point is a function of t, so if I differentiate both sides, I get the velocity of the wave. Okay. How do you get the fu at both t equals 0? Where? You mean this? I mean, yeah, where was it? I mean, u is equals to kx minus omega t. So at t0, plot this graph. At t greater than 0, plot this graph. Right? Where u is equals to kx minus omega t. Okay, so I have y is equals to fu. So it's just yeah, at t is, so this is at t is 0, so it's just y is equals to k squared x squared. So because t is 0, because if t is non-zero, then y is equals to kx minus omega t squared. Because when t is 0, this term is not there, that's why you got k squared x squared. Yeah, so I just talked about this. So for some fixed variable, when I differentiate t, x is constant. Yeah, so you guys get it, right? Again, if you don't get it, also never mind, because it's actually not the main point. The main point is the wave equation, right? So the wave equation is here. And what I wanted to say was, any function where the graph is moving to the right, right? So any function where the graph is moving to the right, it will satisfy this equation. Right, so any function with the graph moving to the right. Yeah, actually that's a nice way to put it. Rate of change of f as t increase. Correct, that's a nice way to explain this. More of a VT graph. Kind of, yeah, but right now, for this chapter, I will seldom draw the VT graph. Okay. So the main reason I want to derive this, right, is that this is page 4, this is page 5. So that means the lesson that we want to take home from today is that if a system satisfies this one, then the solution is f of kx minus omega t, right? So yeah, then, and the graph so the shape of the graph is moving at speed. Okay, v is equals to omega over k. Okay, so that is the amazing thing about this. So all this function, right? So let's say so just now I was telling you the example of kx minus omega t, right, was a quadratic function. Okay, so this shape moving to the right, right? Or another function, kx minus omega t is equals to sine. It's also moving to the right. Another function, kx minus omega t, I don't know, e to the power of kx minus omega t. Right, so all this function, all of this, they satisfy the wave equation, and they all if you plot the graph, you see the shape will move to the right at speed v, which is given by omega over k. Right, so this one I had shown you already. So this is the shape of the graph that is moving to the right, right, and then the sine function is basically a sine function that is going to the right, and then this is the exponential function that is going to the right. So any function, right, where your argument or your variable is kx minus omega t, is just the shape of the graph that is moving to the right. So as long as they satisfy this equation. Okay, so if you can try it for yourself. If you don't believe me, you differentiate with respect to t twice, and then you differentiate with respect to x twice. For this, you do the same thing for here as well, right? So it's for any function. Well, to be math people should say that, you know, it's any continuous and differentiable function that will satisfy this condition. The gradient vector of a function. Correct, yes. So this one is when you learn multivariable function. If you differentiate with respect to multiple variables, yeah, a 3-dimension. So right now, right, I have a 2-dimensional coordinate system. I have 2 variables, t and x. Yes, this is what you will do in calculus 2. In calculus 2, you will differentiate x, y, z. Yeah, you mean the gradient, right? So the nabla, the gradient symbol, right? So this one is just d dx, d dy, d dz. But don't worry about this yet, right? So this one is the math student know this. For the physics student, is next semester calculus 2, right? So yeah. Okay, any questions so far? Z is amplitude dependent. But actually, yeah, you are getting it now, right? So so this one is not my Z. Yeah. So I call this my vertical axis. So I'm calling this Y at the moment. But my variables are x and t, right? There's no z here at the moment, and I'm just defining u as kx minus omega t, right? So u is another 2-variable function. Right now there's no z. There's no z here. Oh, is it potential energy? Horizontal axis. Oh, x lah, you mean? Yeah, x. Okay, so so you already used this for potential energy in thermodynamics. Oh yeah, no, our potential energy I got showed to you before, right? Yeah, I did show this to you before, but it's just to show. Yeah, it's not our main concern for this semester. Okay. Basically, it's not our main concern, but our main concern was if I have if my potential energy depends on x and y, right? I can differentiate with respect to 2 directions, and therefore I can get the force in the x component, and I can get the force in the y component. So this is how we so we do not introduce this symbol yet, but I can calculate my force in the x direction by differentiating with respect to x, and then my force in the y direction by differentiating this with respect to y, right? And then so this is my horizontal component, this is my vertical component. This was what we did last time when we were talking about potential energy. Okay. Correct. So after everything we were talking about, right, is, yeah, I'm just want to convince you that a function with a moving graph can be described by this wave equation. Okay, so anything that satisfies this wave equation, right, will have this function given by the moving graph, right? So I drawn this, right? All this picture that is moving, the moving graphs. Z. Oh, so what you mean is, yeah, I was calling this y, f of u, f x t. Yes, yeah, correct. I was calling the vertical direction y, this direction y. Okay, so where are we now? So it's already 10:52. I don't know if got time to play guitar later, because we still need to talk about waves along a string. Okay, so what I'm going to do now is, well, I have tried to convince you guys that wave equation is satisfied by this. So, and if a system satisfies this wave equation, then the solution will be given by these wave functions. Okay, and right now I'm going to do next is, I have a string, right, the guitar string kind of thing. The guitar string will actually satisfy this wave equation, and I want to show you why. Okay, so let's see why. Okay, so then, yeah, then we have to go faster lah, right? So let's consider a string. Actually, right, what time is it now? Now let's take a 10 minutes break, because this is kind of a new topic. So let's take a 10-minute break, then 11:03 we shall continue. Okay, so yeah, then meanwhile I will draw the picture and things like that. Okay, so let us take a 10-minute break. Okay, stop recording. Start here. Okay, so let's talk about the waves on the string. And full screen. So again, right, there's gonna be a lot of scary math, and if you don't follow, also never mind. This one is only just to show you where it came from, and at least you see it coming from somewhere, and the equation doesn't appear out of nowhere. Okay, if you can follow, never mind. If you can't follow, never mind. If you can follow, then good. Because I want to derive the equation that is obeyed by a wave traveling along a string. So I'm going to consider a string with uniform mass per length. Okay, so the string, right, is, I can draw the sketch. I will briefly sketch the string. So the string is, let's say, yeah, it's vibrating along, right? So let's say this could be my guitar string, okay? And I'm drawing it a little bit bigger to make it look thicker, okay? And I will consider a short section on the string. So let me consider one segment, okay? And let's suppose that the segment here is about dx. So this is position x, this is x plus dx. So let's say the segment is delta x, right? And then the mass of the segment is delta m. So this is a string of uniform mass per length, right? So this is the whole string, but I just take one part. Okay, so the mass per length is, well, if I take the small mass divided by the small length, it is a constant. It's given by mu, right? So it is a constant because it is a uniform string. And as you can see, right, my guitar, my rusty string is made of metal, that's why it's rusty, and the whole thing is metal, so the density will be uniform. Okay, so this is I want to study the forces acting on the string. So because this is a string, right, I consider this as one piece of mass, and the rest of the string is like a string, right? And if it's a string, it will experience force, in other words, tension. So on this side, it will experience the tension coming from this rest of the string. So this one is experiencing a force of F2, and this part it will experience a force of F1. Okay, so I'm gonna call this position 1, and this point is point 2. Okay, so at this point it will experience the tension, I will call this F2, and the tension of F1 over here, right? So do you guys follow the reason why I draw this free body diagram so far? Okay. Not uniform after rusting. Yeah, unfortunately that's true. Yeah, so my string is probably no longer uniform. The free body diagram is the one small piece of string. It's for the one small piece of string. Yeah, so the dot is the whole string, but I just take one piece, one small part of the string. Okay, so one small part of the string, and this is the so I take the whole string, and then I look at one part of mass delta m and a small length delta x, and then it's attached to the rest of the string, so it will experience the force coming from the rest of the string, right? So if I take some piece of string, right, this small part, then if it's stretched, then this piece will I mean the whole thing is same color, right? So this small piece will experience a tension from the rest of the thing, right? It will also experience tension from this side, right? So this is the net force acting on one small piece of string. Okay. Oh dear. We are not talking about energy yet. We will at the moment we are talking about forces. Okay. So let us, because this is a x and y direction, so let us resolve our forces. Okay, so this is my x direction, this is my y direction. So let us resolve the forces. So F2, right, I can resolve horizontally. So this is F2 in the horizontal component, and then this is F2 in the y component, right? And then this one also I can resolve. So F1 in the y component, so it's down, and this one is to the left, F1 in the x component. Okay, so since we are talking about the we are assuming transverse wave. Okay, so we assume transverse wave. So transverse wave, and let us assume all horizontal forces are 0. Cancel each other. Okay, so that means F2x is equal to F1x. Okay, so these two are equal. So let me call this horizontal direction to be the F0. Okay, so this is approximately equals to the tension along the string, the horizontal tension. Okay, so the left and right are the same tension. So the whole string is having the same horizontal tension. So if you look at one piece, right, then on this side is tension F0, on the other side is also tension F0, so they cancel each other, right? So there's no horizontal motion. Okay, so I only consider the vertical motion. So how do we get the vertical motion? So this is point 1, right? So this is point 2, right? And to calculate the motion, right, let me show you how to get the gradient. So this is on the xy axis, and my string is basically like a line. So let me draw the gradient at point 1. So how do we calculate the gradient, right? So the gradient is the derivative of this with respect to x, right? And then if at point 1, that means I calculate at the position x. So if by the the congruence of the triangle, it is equal to the f1y. The gradient is this height divided by this height, right? So f1y over f1x, the magnitude, right? And this divided by this, it will give you the gradient of this slope. Okay, so it's going to be F1y. The horizontal force, I'm calling this 0, right? So in other words, I have F1y is equals to F0 times partial y partial x, and this partial y partial x is calculated at x equals to 0. Okay, so this is gradient at 0.1, and then you do the same for gradient at 0.2. So gradient at 0.2 is the derivative at 0.2, the x coordinate of 0.2 is x plus delta x, right? And then the gradient is the vertical divided by the horizontal, so I got F2y is equals to F2x, and then F2x is the same as the horizontal tension, so I got F2y over F0. So in other words, my F2y is equals to F0 partial y partial x, and then this is at x plus delta x. Yeah. So I let you digest this first. Let's see if you agree or not. If not, ask me any question. I need to clear my nose again. Yeah, I'll be back. Okay, so everyone's okay, huh? Yeah. Yeah, what's the question? The gradient F2 minus F1, that is just the difference of the force, right? So F2 and 1 are different points. So, oh, you got it? Yeah. So I'm just using everything on point 2 to calculate the gradient on point 2. And then the gradient at point 1, I use everything related to point 1 to calculate the gradient there. Okay, so now, right, okay, so this is for 2 points, but now I will take the net force on the whole thing itself. So let's take the net vertical force. Okay, so my vertical force in the y direction, right, the net force in the y direction is the upward force minus the downward force, right? So is F2y minus F1y is going down, so minus F1y. Okay, so this is my net force. Yeah. Am I recording? Test? Yes, I think so. Okay, so I got this now. Then this is my net force, right? So my net force is, by Newton's law, it is the mass of the object times the acceleration. So I'm talking about the vertical direction, so I'm talking about the vertical acceleration. And then what is the right hand side? The right hand side is F2y minus F1y, and F2y is over here, F1y is over here. So it's this minus this. Minus F0 partial y partial x, and then x. And then this, both of these terms can factorize out the F0. So I got the partial y partial x evaluated at the point 2, and partial y partial x evaluated at point 1, right? And I got this equation now, and this is delta m. So what is delta m? So delta m, right? Well, delta m is related to a string of uniform length. So delta m is equals to mu delta x. So therefore, I put this inside here, right? So I got mu delta x, a in the y direction, and is on the right hand side is equals to this thing. So partial y partial x evaluated at this, and then partial y partial x evaluated at this point. Okay, and then also my acceleration is just the second derivative of y with respect to time, because y is the position of my string, right? So it depends on time. So if I differentiate the position of the string with respect to time squared, it's the vertical acceleration. So I got this. Okay, so now I can rearrange everything. So if I rearrange this, I will have dt square. The mu delta x, I bring this down, so I got f0 over mu, and then this whole thing is partial y partial x, x plus delta x, minus partial y partial x evaluated at x divided by delta x. Okay. The gradient for the force is moving. Is it moving? The slope. Yeah, so this is the slope of the graph. Gradient means the slope of the graph. Just the slope. Yeah, just the slope. Okay. Okay. So now, now we consider infinitesimal point, right? So this is the equation for a segment. Then what I'm going to do is I'm going to consider where delta m is infinitesimally small. So take the limit 0. Okay, so that means partial y, partial t square. These are constants. And then I want to take the limit of delta x to 0 of 1 over dx, and then bracket dy dx, x plus delta x. This is partial y, partial x, evaluated at x. Again, right, if this part you don't understand, never mind, because it's supposed to be your calculus too. I just want to show you is partially is because to show you where the wave equation is coming from. But for the math student, if you've taken the calculus 2 already, right, you will realize that this is the definition of the second partial derivative with respect to x. Okay, so what we have now is that my partial y partial t square is equals to f0 over mu dy dx square. Okay, so this is the wave equation. We actually got the wave equation, right? So that is actually very important. Even though the steps are not important, I leave it for you to learn it in calculus 2. But the important thing is we have considered the free body diagram of a vibrating string, right? By drawing the forces and everything, we do the calculation, and actually it satisfies the wave equation, right? So, and then what is this? This is a function y. So the function y is the vertical position of the string. So the string satisfies the wave equation. Okay, so the motion of the string, right? If you have the so that is it satisfies the wave equation. So the variable y, right, is your it is your guitar, right? So if your guitar is in equilibrium, no space. So if your guitar is in equilibrium, right, the y is 0 everywhere. But if I move the guitar a little bit, so there's a vertical displacement, right, and it changes over time, right? So that is what I mean by the y, and it satisfies the wave equation. Excuse me. Yeah, so you guys are talking about Manglish. Thanks. The dust. So I think I know why lah. I haven't touched my guitar for so long, right? It collect all the dust. No wonder lah. That's the culprit. So it satisfies the wave equation. It satisfies the wave equation, and then the velocity of the wave v is well, remember, right, this part is supposed to be v squared, so the speed of the wave is the tension over the mass per length. Okay, so it is the speed of the wave is equals to tension on the string divided by mass per length of string. Can you see? Okay, so actually, right, speaking of guitar, they actually give you the tension. So they like this the spare strings. So they actually give you the tension for all the necessary strings over here, and then the length of the string is just the length of the string, right? So that's easy. And then the different material for each of them, they have the mass per length. So even my spare string is starting to get rusty already. Oh my god. Ugh. Yeah, very terrible. If the string in vacuum, it will vibrate. Yes, just that there's no sound. Guitar not absorb the energy, but actually this is what we want to calculate next, is that the energy is flowing through the string. Energy is flowing through the string. Okay. So any other questions so far? Yeah. So yeah, if you do it in space, right, there's no sound, but the string can still vibrate. Just that we only hear it because of the sound in the air. So if you do it in space, no sound, but it's still vibrating. It's still a force. You can, because it's the force is tension. Okay, so the next thing we want to do is the sinusoidal wave. Okay, so for the sinusoidal wave is for the specific solution where my f of u is sine u. So sinusoidal wave means I consider a specific solution. Okay, a constant sine u. Okay, so here we consider a solution to the wave equation. Okay, so my solution, right, yeah, my wave equation is satisfying this, and I have shown you just as at the beginning of today, is that any function of u is a solution to the wave equation. So where my u is equal to kx minus omega t. So it works out the wave equation, and it depends on two variables. So A is a constant, and I will consider sine of kx minus omega t. Okay, so this is my wave equation. Okay, so I will consider this as my specific solution. Not propagation. Yeah, so standing wave, right? Standing wave, we will come to that later, but all of these waves are solution that's propagating along the string, including standing waves. Okay, so I have this solution. I will consider this specific solution, right? So this is sine kx minus omega t, and as you can see, right, this solution is periodic in x. Okay, because this is a sine function, right? Sine function, the function, if I increase by anything 2 pi, it will repeat again, right? Another 2 pi, it will repeat again and again. So periodic in x, as you can see, right, it repeats after x is increased by 2 pi over k, right? So if you look at this, right, if this number increase by 2 pi over k, it will increase, it will start to repeat, and this will become the wavelength. Okay, and it is also periodic in time, because time is also inside the sine function. So as time increases as well, it will also start repeating, right? So this will repeat. T increases by, well, this is omega, right? So it's 2 pi over omega. Okay, so from here we define our quantities for our sinusoidal wave. K is 2 pi over lambda, right? So I define k to be 2 pi over lambda, where k is what we call the wave number, and this lambda, right, is the wavelength. Okay, and then we also define omega to be equals to 2 pi f. This is the same as what we did last time, right? So omega is the angular frequency, and f is just the frequency. Okay, so how does this graph look like? So this graph, right, is a sinusoidal wave that is initially a sine function, right? So this is t equals to 0, and then as time goes on, right, the f I was showing you just now is the sine function. The whole graph will start moving to the right, right? So maybe it looks like this, right? So this is t greater than 0. So you will, the shape of the graph will move like this. Yeah, correct. With a coefficient, yes. And the coefficient is the amplitude. Yeah. So actually sine u also can, and cosine u also possible, but for now let us take cosine u. And by the way, yeah, so A is the amplitude, the coefficient that you mean. Okay. And this part is also another important thing. We call this the phase. Now it's too bright. Okay, so this is our sinusoidal wave. K is the, yeah, K is the special quantity I define to be wave number. Okay, so wave number. And then if I draw this picture, right, this picture is, my y-axis is over here, this is my z-axis, right? So as you can see, right, the wavelength is the distance for one cycle. So from here to here is the wavelength. So this is wavelength, and we call this lambda, right? And then the k is just defined to be 2 pi over this length. right? So the one wavelength is like this, right? So two wavelengths is twice, one time, two time, right? So it's twice, and then yeah, right? So you can even do half a wavelength is, well, it's half of this cycle, so it's like this. Okay, got it, huh? Okay. Okay, so for this wave, right, it describes a sine function that is, well, the shape of the graph is moving over here, but if you follow each point, right, if you follow every individual point, so a particular individual point will be going up and down by the periodic motion, right? And then just the shape of the graph, it looks like it's going to the right, but if you look at the guitar string, right? So the guitar string, if you follow every point in the string, each point of the string is moving up and down. So from here we can calculate the vertical velocity or the transverse velocity, right? So as the string moves, right, so it's going to vibrate up and down. So I can calculate the this thing, right? So the transverse velocity I will calculate the wave is, well, is partial y partial t, right? It's just taking the y position, differentiate this with respect to t. And what is my y? My y is a sine this. So if I differentiate this with respect to t, I get negative a cos kx minus omega t, and then omega, right? So that's a chain rule. Okay, so this is my transverse velocity over here. And then the propagation velocity, or we call this the wave velocity, is the moving in the x direction, right? So remember, right, the wave got two velocities, the direction of propagation velocity and the velocity of the disturbance. So this is the disturbance velocity, is going up and down, but the shape of the graph is going to the right, and we have shown just now is given by omega over k. But I have defined omega to be 2 pi f, and then the k is 2 pi over lambda. So I can cancel this, and I conclude that v is equal to f lambda. Okay, so this is the speed of the wave, is the frequency times the wavelength. Let me fix my nose again. No. Okay, so yeah, these are the two velocities that we have on the wave. Where are we now? We are page 7. Page 8. Any question? Is there a phase difference? Right now there's only one wave, so every point has one phase. Normally we calculate phase difference for different waves, and we will actually do that later. Right on the diagram. Yeah, so it's how fast is this point moving? Okay, why I call this Vx? This is V1. V1. Yeah, so every point has a velocity. Every point has a velocity. Okay. So now let us calculate the energy through a wave. Vibrating string. Okay, so again, right, let us consider a vibrating string. Okay, and then let us consider a segment of length dx, and then this is having a transverse velocity vy. So we calculated this already, right? So the transverse velocity of this point is omega a cos kx minus omega t. Okay, so let's consider a segment of mass dm, and then therefore the short length is dx. So therefore dm dx is mu, is a constant. Okay, so I'm going to use this later, and dm is actually mu times dx. Okay, so what I'm going to do now is I'm going to calculate the energy of a vibrating string, right? So a vibrating string actually carries energy. So to do this, let us calculate the kinetic energy. So this is moving up and down. So we can actually calculate the kinetic energy using half mv squared. So the kinetic energy, I guess everyone can remember the formula for kinetic energy, right? So it's half mv squared, right? So this is moving in the y direction, so I got y here. And if the mass is small, then the kinetic energy is also small, right? Infinitesimal. So I can calculate the infinitesimal kinetic energy. Due to motion of an infinitesimal mass dm is given by what? So it's dk is equals to half dm, and then the velocity of this segment. Right? So we can use this formula to calculate the kinetic energy. So let's see how to calculate. This is half, and then dm is mu dx, so let's just put this straight away here. And then vy square is this thing here. So I got mu dx, and then vy square is the square of this, so I got omega square amplitude square cos square kx minus omega t, right? So this is dk, and what I want to do is I want to calculate dk dt. Okay, so dk dt is basically differentiate both sides with respect to time. Omega square a square cos square kx minus omega t, right? And this is the position, well, this is the propagation velocity, so this is v, right? So the velocity in the wave propagation velocity. So I have found that my dk dt is equal to half mu v, and then I got omega square a square cos square kx minus omega t. Okay, then so this is the rate of kinetic energy transfer through the point of dx, because I'm calculating how much this kinetic energy is changing over time of a particular segment. Okay, so this is depending over time, and usually, right, for a vibrating string, this function oscillates very fast. So what I'm going to do is I want to calculate the average rate of kinetic energy transfer. Okay, so I want to calculate the average over time, because this function is, all these are constants. So all these are constants, so no need to change anything. So omega square a square cos square kx minus omega t, constant. So constant is not affected by the average. Minus omega t. Okay, so this answer, right, is actually half. Okay, so average of cos square is half. So the answer is half. So actually, right, the average of kinetic energy transfer is 1/4 mu v omega square a square. so this one was earlier, right? Yeah, so the vertical v is the velocity. Okay, so again, right, this part, yeah, I'm sorry because today I have to mention a lot of things that is you actually learn it later, but I'm just using it to calculate something. So the average of kinetic energy transfer is given by this, and then I will not go through the details, but the average rate of potential energy transfer is the change of potential energy of this point of the string, right, is going to be given by something similar. So it's mu v omega square a square. So the total energy change, so the total rate of energy transfer is dE dt is equals to the kinetic energy, right? So it's E is total energy is Ke plus potential. So it's this thing. And these two are the same. So the total rate of energy transfer is equals to this plus this. So it will give you half mu v omega square a square, right? So this is actually, if you notice, right, rate of energy transfer is actually the average power. So average rate of energy transfer is average power. So in other words, there's a power being transmitted through a vibrating string. So it's half mu v omega square a square. Okay, so today's for today only lah. For today, the math is very complicated. So if you don't follow, never mind. I just want to convince you of something only, just to show you that this formula didn't come out of nowhere. All right, there's some reason behind all this formula. Yeah, so I went through a bit fast. You get the average by integrating it, correct? Yeah, you didn't miss anything because this is given, or it can be shown. And yeah, even though I show you the complicated math, this one is even worse, so I don't want to show you, right? So there's two terms here. I did not show you why this is equals to this. I just give you, right? So this is the one that I give you, yeah. But the rest is calculated. But if you add up everything, then I got the average power. Okay, so you didn't miss anything. Yeah, the interesting thing is not to say it's not conservation, because dE dt is, for this case, is non-zero, right? It's non-zero, and the reason to imagine is actually easy to understand, because if you remember, right, we define wave to be a disturbance propagating through a medium. So I have something that is moving to the right. Okay, so something that's moving to the right. So that means initially, you know, this part of the string is not moving, but then if I move through, it will make this string move. So energy is flowing from left to right, right? So there's no conservation of energy. There's energy passing through the system. So that is what I want to show you here, right? Yeah, so back, since I have the guitar, right, back to the guitar again, right? So right now, the nothing on the guitar is moving, so there's zero energy on my strings, okay? But if I were to pluck the string, it's too small, can you see? Yeah, if I were to pluck the string, right, it's too small on the webcam, but it's too big over here. Okay, so right now nothing is moving, right? My rusty string is not moving, but if I pull the string a bit, I'm giving it some potential energy, right? then I let go. So now I got potential energy and kinetic energy interchanged with each other. So this is what we will calculate next, is that if I plug the string, right, so the energy is actually moving back and forth along the string. This is how we get the standing wave. Right, so energy is passing through the string. To reach the equilibrium energy transfer is the same. Yeah, but right now the system is not exactly in equilibrium. It's not exactly in equilibrium. At every instant, it's not in equilibrium. Okay. Right. Yeah. So your earlier question, I think I forgot to answer. Yes, you integrate over one period. The answer is half. Yeah. So the area under the cosine square is half. The process. Yeah. You can say that. Yeah. The process of reaching equilibrium. Yeah. So it's a non-equilibrium process. Okay. So to finish off, right, let us work one example. So example 9.2.1. Where are we? Yeah, so let us solve this example. A string of linear density missing a y is given by this mu, right? So let me write down the info here. So we are solving example 9.2.1. 9.2.1, we have mu is given by 525 grams per meter. So this is in grams. The tension on the string is 45 newtons, right? A signal sent through as a sinusoidal wave with a frequency f is 120 hertz. And then the amplitude is 8.5 millimeters, so times 10 to the minus 3 meters. At what average rate does it transport the energy? So these are the information given. And our formula for power transmitter, right, contains a V. So I need to calculate the V first. So the V is given by the tension over the mass per length. So we can put in 45. Mass per length is this many grams, so it's 0.525 kg. So this is 9.26 meters per second. So the speed along the string is 9.26 meters per second. And then we calculate the average power of energy being transmitted is half mu v omega square a square. So put in all the values, right? So mu is 0.525, v is 9.26, omega square is 2 pi times the frequency square, and then the amplitude square is 8.5 millimeters, so 10 to the minus 3 square. So all these are numbers, right? So you can use a calculator to get your answer. The answer is 100 joules per second, or 100 watts. Okay, so yeah, so hopefully I hope I didn't scare everyone too much with math. The derivation have a lot of partial derivatives and things like that, but we just want to, right now I just want to convince you of the concept, right? There's energy flowing through the string, and that is given by this formula. Okay, so and this much energy is passing through the string per second. 100 joules of energy passing through the string per second. Okay. Yeah. Okay, so is there any other question? So yeah, so if not, then the next topic is superposition and standing waves. So we will yeah, so I guess we're out of time, so we will continue this on Wednesday, right? And let me also say one more time before we forget that our next quiz is next week, right? So our quiz will be about chapter 8 and 9. Okay, so yeah, so that's all for today. Let me stop the recording. Right, so any question you can stay and ask me here. Otherwise, we continue next week. Yeah, lunchtime. I'm hungry too. Yeah, so let's go for lunch. Everyone can exit and go for lunch. I will stop recording here.